Hello. Here today I am going to explain the intuition behind the variation in x. So in the previous video, I have explained why you need a large enough variation in x to have a accurate estimator. I will explain the same thing with a different graph that I used for the PhD students. So it's a higher level econometrics, but still intuition is the same. So I am going to recycle the same slides for you guys, and I believe it's intuitively simple. So think about the regression line here. Same x, y, and simple. I use slightly different notation there, alpha and beta, and instead of u I use epsilon, but it's error term. This is error term, and nothing is different. Intercept is alpha, slope is beta. True regression line goes like this, red. And suppose that you have two observations, but those two observations have their own error terms. So error term, the first observation have an error term of epsilon 1, and the second observation has its own error term of epsilon 2. So I'm going to maintain the same amount of errors. So the epsilon 1 has a negative error, and epsilon 2, the first observation has a negative error, so lower than the regression line. But the second observation has a positive error, which means it is above the line. Then using these two observations, we would like to estimate the red line. So in practice, from the data, this is what you observe. You only have scatter plot. You don't see where is the true line and how much is the error term. So this is the only thing you can observe from the data, scatter plot. And then your estimator is this. You estimate the slope by connecting these 2 points when you have 2 points. When you have more points, then you use more complicated least squares method, but the intuition is the same. We would like to draw a straight line that best explain the scatter plot. So this is your estimated slope, but then now compare your estimated one and the true one. The true regression line is red, and this much angle is the estimation error. So estimation error is inevitable. There is no way you can do anything with this error. Just you have to take it. But what we are going to do here is we are going to consider what would happen if you had smaller variation in x. So as you can see, the base is now much more narrow, much narrower. Still, I assume the error term is of the same size. Error terms are of the same size as before. So the first observation is negative, as much as the same degree of the previous example, and the second observation is positive and exactly same magnitude. And in this case, the only difference is x moved inside to each other, and then your estimated slope is like this, and estimation error is much larger, right? It's clear. And as you see, as I said, the intuition is simple. The base is too narrow and when it's too narrow, small error will cause huge errors. So this is the intuition that I would like to give you in the previous slide, which is very important. And so think about this example. So same idea from this graph, but it is from the textbook, and I made up my own explanation, which I believe is better. I think better than what the textbook does. So I introduced you. And so summary, I don't think it's important. You don't need to memorize any of that, but you need to understand the key points. It is unbiased. OLS estimator is unbiased. And second, as you have larger data, more sample size, then you can do better. Your variance will decrease, and in the limit it will be going to 0. So proportional to 1 over n. That's the point. So unbiased, first point. The second point, 1 over n. And third point, which follows from the first 2 points, is that it's consistent. So as the sample size goes to the limit, your estimator will be certainly correct without any error. So really nice. And finally, what's most important and most useful thing is this one. Central limit theorem. By the central limit theorem, your estimator minus the true parameter. The mean is the true parameter, right? And because we know this, the true parameter standardized by the sample standard error. By the standard error. So square root of variance is the standard error. So if you standardize the estimation error divided by standard error, it is normally distributed. So see that, you need to see that the numerator captures the estimation error and the denominator captures the standard error, right? So it is normally distributed. So which means, and because the standard error is calculated by the program, so which means you know how big the standard error of your estimation error is. You know the standard deviation of the estimation error. That is the standard error. So, and as I said, this is the basis, the starting point for many inference methods that's coming in the next chapter. In the next chapter, we are going to do hypothesis testing. We are going to do confidence interval things in the next chapter. So we are going to rely on this. So you, instead of reading the mathematical equations, still you need to understand something. You need to study something. The results are important. I want you to get the essence of the ideas. So I skipped a lot of equations. Okay, this is it. And my plan is so this will be posted on Monday, on the 22nd, February 22nd. And I hope to check what's going on with the stata distribution. I'm going to send you an email, and whenever stata is ready, I will post stata introduction, because we need to do that as soon as possible, because the homework is waiting for us to do the stata. So I will give you an email. See you later. Bye.